Welcome to the SAR channel, where sound and audio are demystified. In analog audio, there's no way to fix mistakes. If the sound wave gets distorted or interrupted, it's usually damaged for good because an endlessly changing waveform can't be reconstructed accurately. In digital audio, things are different. Since digital signals use simple zeros and ones, it's much easier to detect and fix errors. When a wrong bit appears, it can be flipped back to the correct value. This works because digital audio data is encoded with extra information called redundancy that helps check and correct errors. If an error is found, the system can either fix it completely or hide it by blending nearby data. This makes digital audio storage and transmission far more reliable and efficient. Strong error correction systems even allow for lower signal-to-noise ratios and looser manufacturing tolerances for mass-produced media. Error correction is also essential because audio storage media are packed with data. Even a tiny flaw or dust particle can destroy thousands of bits. Thankfully, digital audio can handle small errors without ruining the listening experience. Still, because many audio systems operate in tough conditions, error correction is vital to prevent noticeable sound problems. In short, error correction protects the integrity of digital sound, a safeguard that analog systems never had, and it's one of the key reasons digital audio works so well. Errors can appear at any point in the digital audio process. Problems like quantization error, converter nonlinearity, and jitter can limit sound quality. Using high-quality parts, smart circuit design, and precise manufacturing helps reduce these issues. Error correction mainly deals with stored or transmitted data, where problems are hardest to control. In these stages, harsh environments can easily damage the signal. Except for design flaws or hardware failures, the most serious errors usually happen during recording or transmission. These errors corrupt data and cause faulty audio. The main cause is signal degradation, a defect or weakness in the medium that makes the signal drop momentarily. Transmitted signals are also exposed to interference from human activity or natural events. Noise, crosstalk, weak signal strength, fading, and reflections can all create errors. Defects in storage media or disturbances during transmission can make data bits flip incorrectly. The impact depends on the type of error. A single bad bit is easy to fix, but a long string of errors may be impossible to correct. Errors in small bits of data, least significant bits, may go unnoticed, but errors in major bits, most significant bits, can cause a loud volume jump. Serious errors often cause bursts of noise, distortion, or a short silence. In extreme cases, lost or invalid data can create clicks or pops as the digital-to-analog converter jumps to a new level based on wrong data. When errors happen one at a time, they're called random bit errors, and they're usually easy to fix. Burst errors, on the other hand, affect many bits at once and need more advanced correction. The burst length shows how many nearby bits the system can fix together. Since both random and burst errors can appear in the same medium, error correction systems must handle both. Because every medium has its own weaknesses, error correction must match the application. Storage, wired, and wireless systems each face different problems. The method used for error correction also depends on the modulation code that transmits the data. For example, sealed magnetic hard drives resist dust and damage better than CDs. In wired systems, many factors, such as limited bandwidth, noise, signal reflections, poor cables, or connectors, can distort the data. Cables also act like low-pass filters, reducing signal bandwidth and causing intersymbol interference, where fast signals blur together and don't reach full 0 or 1 levels. Low-frequency noise can also add jitter, disturbing the timing of data. Fiber optic cables are much better protected from radio interference and signal problems than copper cables. Wireless audio systems, however, face many kinds of errors. Since they use radio waves, their signals can weaken or fluctuate, causing poor reception. Other electronic devices can interfere with these signals, and reflections from buildings can cause multipath interference. Signal quality also depends on antenna placement, distance, and even weather or solar activity. Physical obstacles can further reduce signal strength and reliability. Several measurements are used to describe how accurate and reliable digital data is. The bit error rate, BER, shows how many bits are wrong compared to the total number of bits received. It's calculated by dividing the number of incorrect bits by the total bits. The block error rate, BLER, measures how often a block or frame of data contains at least one uncorrected error. It's often expressed as the average number of errors per second, usually measured over a 10-second period. Since burst errors happen irregularly, BER alone can't describe them well. In these cases, systems may measure errored seconds, which count every second that contains one or more errors. This doesn't show how many bits were affected, only how often errors occur within given time intervals. When building error correction for digital audio, it's important to estimate BER and BLER accurately. If the estimates are too low, some errors may remain uncorrected. If they're too high, too much bandwidth will be used for error correction instead of actual audio data, reducing sound quality. In any case, the goal of a digital audio system is to detect, correct, and minimize errors as much as possible to preserve the integrity of the sound. Different applications need different kinds of error correction. Designers must decide how well the system should handle random and burst errors, how much extra data, redundancy to add, how to limit undetected errors, how long a burst of errors it must fix or hide, and how much the encoder and decoder should cost. In digital audio, if an error can't be fixed, it's usually hidden. But if the system fails to detect an error, it can cause a noticeable click in the sound. Since some errors are predictable and others are not, correction systems must use a mix of methods to deal with them. Storage and transmission systems often introduce errors, so extra data, redundancy, must be added to help recover the original signal accurately. However, redundancy alone isn't enough. Smart coding is needed to detect and fix mistakes. In theory, a system could detect and correct every single error, but this would require so much redundant data that it would be impractical. A good digital audio error correction system therefore aims to keep the audible error rate very low while using as little redundancy and processing power as possible. An error correction system works in three main stages. Error detection uses redundant data to check if the information is valid. Error correction uses redundancy to replace wrong data with correct values. Error concealment is used when errors are too big to fix. It fills in missing data with approximations to make the sound natural. If concealment isn't possible, the system may mute the output to stop harsh or distorted sounds caused by unreadable data. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. All error detection and correction methods rely on redundancy, which means adding extra data that doesn't carry new information but helps check accuracy. The higher the risk of errors, the more redundancy is needed. Redundancy is essential for reliable communication. If data is sent and received only once, there's no way to know for sure whether it's correct. Without extra information, we can't detect or fix errors. Therefore, additional data must be included so that the receiver can recognize when something has gone wrong. However, since this extra data is created and transmitted along with the main data, it can also be affected by the same errors. The goal of error detection is to encode data in such a way that any corruption or loss becomes noticeable. One simple method is to repeat the original message. For instance, each word could be sent twice. If the two versions differ, one must be wrong, but it's impossible to tell which one. Sending each word 3 times improves accuracy because if 2 copies match, they are probably correct, and the third is wrong. Yet it's still possible that all 3 are wrong. The more repetitions used, the more likely errors will be detected, but this also creates much more data to send. Too much redundancy increases the data load and can even introduce new errors on its own. In real-world systems, error detection adds extra data that helps quickly check if something went wrong. One simple method is called parity. However, most errors in practice happen in groups, known as burst errors, where several bits in a word can be affected at once. Because of this, a single-bit parity check, which only checks if the total number of ones is even or odd, is not reliable for detecting such errors. On its own, single-bit parity is not effective for error detection in most digital audio recording or transmission systems. More advanced error-detecting codes have been created to use redundancy more efficiently. A good example is the International Standard Book Number, ISBN, which appears on almost every published book. Each ISBN is unique. No two books share the same one, and even different editions such as hardcover and paperback have separate ISBNs. The ISBN system uses a weighted checksum and compares it with a remainder calculated through modulo arithmetic, similar to how single-bit parity works. This method is very effective for finding errors, and many modern error-detecting codes are built on the same basic idea. A cyclic redundancy check code, CRCC, is an error detection method often used in audio systems because it can spot burst errors that happen during recording or transmission. CRCC is a type of cyclic block code that creates a special parity check word. Like a single-bit parity check, it compares the checksum from the received data with the original one. If they don't match, it likely means an error occurred. The difference is that CRCC uses a more advanced mathematical process, making it far more accurate and dependable. By adding extra data, errors that occur during the storage or transmission of digital audio can be fixed. The simplest method is to make a direct copy of the data. To avoid both copies being damaged in the same way, the extra samples can be time-shifted slightly. While this basic approach works, it wastes a lot of space because it needs too much extra data. A more efficient solution is to use error correction codes, which provide stronger protection with less redundancy. Just like parity bits are used for error detection, extra data is added here to allow both detection and correction of errors. Digital audio is encoded with special algorithms that handle these tasks. When the data is played back, the error correction decoder finds and fixes any mistakes. The encoded data itself forms the basis of all correction systems, which vary in design and efficiency. In general, there are two main kinds of codes: block codes and convolutional codes. Block codes use algebraic methods and work by dividing data into fixed-size blocks, each encoded separately. Convolutional codes, on the other hand, use probabilistic methods and generate encoded data based on both the current and previous input. Some systems combine the two methods into a cross-interleave code, which uses block coding in a convolutional pattern for stronger protection. Block error correcting codes group several data words together into a single block. The system then processes this block to create one or more parity words, which are added to the data. During decoding, an algorithm generates a syndrome word to identify and, if enough redundancy exists, correct any errors. These methods are highly effective for digital audio systems. Error correction can be further improved by interleaving, which mixes the order of consecutive words to spread out potential errors. Block codes calculate parity based on an entire block of data, but they can also form parity from individual words using single-bit parity or a cyclic code. This adds more redundancy and improves accuracy. For instance, a CRCC can first detect errors, while block parity then corrects them. Although there are many ways to produce single-bit parity or its variations, all block correction codes share the same principle. They rely only on the data contained within the block to create their correction code. Cyclic codes like CRCC belong to a group of linear block codes that can also be used for error correction. A special type of block code, called a Hamming code, creates syndrome patterns that show exactly where an error has occurred. For every data word, several parity bits are generated using a unique encoding method to make this possible. Convolutional codes, also known as recurrent codes, differ from block codes in how they handle data. Instead of dividing data into separate blocks, convolutional codes create an encoded output that includes information from both the current and previous inputs, keeping a history of past data. Like linear block codes, the data is encoded and code words are then transmitted or stored. When the data is retrieved, the decoder checks for errors using syndromes to find and correct them. Convolutional codes are usually cheap to implement and perform well even in noisy or high-error environments. However, they have a drawback called error propagation. When one error isn't fully corrected, it can affect later data during decoding. Because of this, convolutional codes aren't ideal for recorded or editable data where precise correction is needed. Instead, they are mostly used in broadcasting and wireless communication, where continuous data flow makes them more effective. Error correction relies on how well an algorithm can handle wrong data. When long errors called burst errors occur, they can damage large sections of both the main and redundant data, making correction very hard or impossible. To fix this, data is often interleaved, spread out or mixed, before being stored or sent. If a burst error happens after interleaving, it only affects a small, continuous part of the scrambled data. When the data is later de-interleaved during playback, it is returned to its original order, but the errors are now scattered throughout the data. This allows valid data around the damaged bits to help the algorithm rebuild the corrupted parts. Interleaving has a major benefit. Without it, the amount of redundancy must match the size of the biggest possible burst error. With interleaving, the largest error in any section is limited by the size of the interleaved segment. So redundancy depends on the segment size, not the burst size. Simple delay interleaving spreads data by delaying parts of it. Many error-checking codes can fix one wrong word per block, but burst errors usually exceed that. Interleaving breaks those bursts up so that after de-interleaving, there's usually just one bad word per block, making correction much easier. Bit interleaving works the same way, letting burst errors appear as shorter or random errors. Each interleaving method needs a buffer large enough to hold all the data while it's being interleaved and de-interleaved. When burst errors occur along with random errors, regular interleaving may not be enough. Even if bursts are rare, random errors can add extra mistakes to the same word and overwhelm the correction system. A good solution is to create two correction codes that are separated by interleaving and delay. When two block codes are combined in this way, it forms cross-interleaving. A cross-interleave code, CIC, uses two or more block codes arranged in a convolutional pattern. This setup is efficient because the error information, syndromes, from one code helps identify and fix errors in the other. Since the exact position of the error can be determined, the overall error correction power is improved. If you've learned anything new so far, please like the video. It really helps the channel grow. Thank you. Reed-Solomon codes belong to an important group of codes called BCH codes, which are a type of Hamming code. They are cyclic codes that can correct multiple errors at once. When used with cross-interleaving, Reed-Solomon codes work very well in audio systems because they can fix both random and continuous errors. These codes are especially strong at correcting burst errors, making them ideal for digital audio and video. When combined with error detection tools like CIRC and interleaving, they become even more powerful. The Cross-Interleave Reed-Solomon code, CIRC, is a powerful error correction system used in compact discs, CDs. It is capable of correcting up to 4 erasures at once. CIRC combines interleaving and parity to make CD data more resistant to errors that can happen during storage or reading. The data is encoded before being written to the disk and then decoded during playback to ensure accurate audio reproduction. The accuracy of data on a CD, as it goes through the CIRC system, can be measured by counting the number of errors. How well CIRC corrects errors depends largely on how the algorithm is implemented. Product codes can perform better than other types of error-correcting codes in modern audio systems. They need more memory to work, but this is usually not a major problem. Product codes handle both burst and random errors effectively and are commonly used in high-density optical media like DVDs and Blu-ray discs. In theory, a perfect error correction system could fix every error using redundant data or exact calculations. In practice, this is impractical because it would require too much extra data. Real-world systems balance this by allowing some serious errors to remain uncorrected while using error concealment to make them inaudible. Techniques like interpolation and muting are commonly used for this purpose. There are generally two types of uncorrectable errors. 1. Errors that are detected but cannot be corrected. These can usually be hidden with concealment techniques. 2. Errors that are undetected or incorrectly corrected. These can cause noticeable clicks or pops in the audio. Undetected errors, often caused by combined burst and random errors, should be minimized. A good system focuses first on reducing undetected errors with the correction algorithm, then uses error concealment to handle the detected but uncorrected errors. After deinterleaving, most errors, even burst errors, are mixed with valid data. This makes it possible to use the surrounding correct data to calculate new values and replace missing or uncorrected samples. This method works well as long as errors are spread out and the data values are related. The simplest form, zero-order interpolation, repeats the previous sample to fill in the missing or wrong one. First-order linear interpolation replaces an incorrect sample with the average of the previous and next samples. Many digital audio systems use a combination of these methods. If consecutive errors occur, previous value interpolation is applied, and the final sample may be adjusted using the average of the retained and next valid samples. For random errors, averages from surrounding valid samples are used. Sometimes higher-order interpolation is applied, using polynomials to calculate replacement values. In practice, third- or fifth-order interpolation may be used. All calculations must be fast enough to keep up with the audio data rate. Muting sets missing or uncorrected data to 0, creating silence instead of letting corrupted data produce unpredictable noise. This is useful for errors that would otherwise cause audible clicks in the audio. Short periods of muting are often inaudible, while clicks are usually noticeable. In cases of severe errors or player problems, muting the output is safer than playing corrupted data. To make muting less noticeable, algorithms gradually lower the volume before the mute and gradually restore it afterward. The volume reduction starts slightly before the error by briefly delaying the audio and signaling the mute in advance. Very short mutes are generally undetectable to the human ear. A key advantage of digital audio is that recordings can be copied without losing quality. Unlike analog copies, digital copies can be lossless, but this depends on effective error correction. While error correction ensures completely accurate data, error concealment does not. In borderline cases, concealment may introduce audible errors, and repeated copying can allow these hidden errors to accumulate. Therefore, errors should be corrected at the source. To ensure reliable digital copying, it's important to use clean media, well-maintained devices, and low jitter interfaces, especially when making multiple generations of copies. In practice, digital audio can be copied very accurately. If a copied file has the same values as the original, it is effectively a bit-perfect clone with the same sampling frequency. Playback will sound identical only if the playback conditions match those of the original file. A simple test for accuracy is to load both files into an audio workstation, synchronize them to the sample level, invert one file, and add them together. If the result is silence, the copy is bit accurate. Any leftover signal shows the differences between the files. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.